Okay, let me start by reminding you what we did last time. So last time I talked about oriented topological circle bundles over manifolds, or especially over surfaces. That's our example. And we defined the Euler class. So to each object like this, you can assign an Euler class, which is some element. We gave a specific co-cycle representative of it, but it's some element of second cohomology of the base space here, which is a surface with integer coefficients. And we proved the Milner word inequality. A theorem that's led to tons of interesting mathematics. And it says that a bundle like this is, one way to say it is flat or foliated. Okay. But another way to say the same thing is that it comes from this construction that we built out of a representation of the fundamental group of the surface to the structure group here, the group of homeomorphisms of the circle. So this is in Hom pi 1 sigma g to homeo plus S1. Or, I haven't stated the theorem yet, I'm just telling you what foliated is supposed to mean. Remember, these had, as well as fibers, they had a foliation transverse to the fiber direction. And another way to say this, if you do bundles, is that this can be reduced to having a discrete structure group. Okay. But none of this language is particularly important, whatever way you want to think about it. The Milner word inequality says that you come from this kind of construction if and only if you take your Euler class and you pair it with the fundamental class of the surface, that should give you some number. And that absolute value of that number should be bounded by the Euler characteristic of your surface, or the negative Euler characteristic of your surface. Okay. So what's this number? If it has to do with the Euler class, let's just call this number something. Okay, so let's call this the Euler number. Of this bundle. And we proved this direction, giving the bound. So we did this. And the secret to this was interpreting the Euler class in the nice way and then computing it using rotation numbers of homeomorphisms of the circle. So the one line ingredient reminder of how to do this is you find a way to compute the Euler number using rotation numbers of homeomorphisms. Okay, so I'll remind you what the rotation number is later on today. And I should tell you at least what the reverse direction of this is. And I sort of made a point to insist that this was really like Milner and Wood's proof, except they didn't use the rotation number. They invented their own functions that did basically the same thing. For the other direction, you want to show that if you have a bound like this, you come from a construction, or the bundle as a circle bundle can be obtained from this construction, and this is basically just the observation that by sort of classical fiber bundle theory, that up to bundle isomorphism, a circle bundle over a surface is completely determined by the Euler class. So if you fix a surface, the types of these things you can have are just determined by the Euler class, but they're Euler classes. It's a complete invariant, and hence by the Euler number. Okay. So you just have to give examples in a very hands-on way for anything that satisfies this bound. A particular representation of the surface group to homeo the circle that realizes that number. Okay. Okay. So to prove this direction, you just can give explicit examples of homomorphisms that realize each possible value, realizing each value. And you might think this is tricky. How am I possibly going to like construct representations of a surface group? I have a relation to satisfy. How are you going to check what goes on? Actually, it's not hard at all. You can even take these to have image in PSL2R. So you can take examples that happen to factor through putting surface groups into PSL2R, and then you can just like write down matrices and compute to see what the product of all the commutators is and what you get for the Euler number. Okay. So this is actually not too hard to do. I mean, like at this point, once you know it can be done in PSL2R, you could ask a computer to do it if you really wanted to. Okay, but you can also completely do it by hand. Milner showed this in his original paper. And if you want to see examples, I can certainly do some for you by hands afterwards. Okay, so this is actually done all the way back by Milner. Okay, so that's the summary of what happened last time. Oh, and I guess finishing up on this thought, why is this the Milner-Wood inequality? Milner considered the case where you just took representations into PSL2R or SL2R. So he studied in this language bundles where the structure group is PSL2R. Or SL2R. These, you know, if you understand one, you understand the other one. Just a double cover of the other. And Wood generalized to representation, to arbitrary topological circle bundles. Okay. Some 15 or 20 years later. And that's sort of the theme of what I want to talk about today. Some parallels or analogies well, analogies and differences, I guess. Between understanding how representations of groups into Lie groups, so like this example, Okay, that's what you would study if you were like a classical representation theory person. So it could be a general group, but we'll think about surface groups as an example to linear groups. But we'll think of PSL2R as an example, or maybe sometimes SL2C as another kind of example. So analogy between studying this and as you would do if you were interested in kind of algebra or representation theory. And representations from discrete groups, again, surface group will be our focus, okay, to groups of homeomorphisms of the circle. Okay. This maybe should give you some hope that if you understand this case, you might be able to generalize some results into this case. Right? This is very interesting for algebraists. This is interesting if you want to do low-dimensional dynamics. And of course, this is interesting if the study of dynamics is just like the qualitative behavior of groups acting on manifolds. This is somehow the lowest dimensional example where your manifold's the circle, and yet it's still like a fascinating world to explore. Okay, so we're going to try and understand all possible representations of surface groups into homey of the circle, or actions of a group on the circle. Hopefully, this construction we did last time, where any such will build you a foliated circle bundle, convinces you that even if you're like a topologist instead of a dynamicist, this is a basic example to study. Okay. And I guess the whole point of this is I want to set us up to give tools for proving a kind of a rigidity theorem about representations next time. So I guess one quick remark before we get started on this. I said here that the Euler number classifies bundles up to isomorphism. This is not true for like foliated bundles. Okay, so maybe a quick note or caution or warning note is that Euler class or Euler number does not classify foliated bundles. So what it tells you is like what is the topological space E with this vibration. It doesn't tell you what's transverse to the fibers. Okay, so maybe a silly example or like a ultra low dimensional example. Okay, to see what goes on here, instead of the base being a surface, let's take it being the circle. So let's look at spaces that fiber over the circle with fiber a circle. So these are all, if everything's oriented, these are all topologically a torus. Right? E is actually always a torus, and it's always a trivial fibration. This is, I mean, if you want to say that Euler classes some element of H2 of the base classifies these, well, there's no second cohomology of the circle. So there's nothing going on here. But we saw that you can always construct these, the foliated version. These come from mapping tori of homeomorphisms of the circle. Use it to glue things back together. And there's lots of ways to build these, and you have lots of very different foliations transverse to the fibers. Okay, so if I build a space like this as a fiber bundle, it looks like here's my S1 in the base and my S1 in the fiber direction, and it's got fibers like this. Okay, and I'm the torus, this is glued to this, and this is glued to this. Okay. Here's one foliation transverse to the fibers. It's just the horizontal product one. Okay, this has all closed leaves. It's like the mapping torus of the identity map. Okay. Here's something radically different. I could take a line of irrational slope, and I could take all lines of a particular irrational slope, and now there'll be no closed leaves. Right? Everything goes on forever. But I could do crazier things. I could take a couple lines or closed leaves, maybe like this or on a slant, and then I could have others that go on forever and sort of spiral around and limit onto these. Okay, and then I guess in the opposite direction I'll come out over here and go like this and something like this. And then you can imagine putting another copy of this on the other half. Okay, and anything crazier in between. And these all have very qualitatively different behavior. They're not isomorphic as foliated bundles. Okay. So trying to understand these objects, okay, so understanding representations of the group of your base. We'll even do just the surface case. Here this was a circle, but that's sort of too easy almost. Understanding these objects, which are foliated bundles, is generally a complicated question. Okay, and saying, oh, well, you know the Euler class, you know everything, doesn't really tell you anything anymore. Okay. This is maybe a bit of a lie. There's one obvious way that two things here could be considered the same, or two things here could be considered the same. Right? If I have a representation of one group into another group, and I just conjugate it by an element here, I won't have really qualitatively changed any dynamical behavior. Okay, similarly, if I have an object like this and I apply the same fiber-wise homeomorphism to each fiber, I'll get just like a conjugate picture. It's just an obvious change of coordinates. So really what we should consider is these up to equivalence by like a fiber-wise change of coordinates, and these up to conjugacy here. Okay, that's a natural notion of you know what these objects are to study. Okay, and our goal is to just understand these. So let me start with some classical and beautiful work of Goldman that sort of kicked off a whole study of representations of surface groups into various linear groups. So this actually sort of approach started in Bill Goldman's thesis in 1984, but the result I'll quote came in 88. And he's studying sort of the same object that Milner was. He's trying to understand representations of surface groups into PSL2R. Up to conjugacy or not, if you like. The statement I'm going to state doesn't really depend on if you quotient by conjugacy. So he's trying to understand this globally. What are all the possible options? And he proves that you can say exactly, you can think of this as a topological space where, say, two representations are nearby. If they send the generators of your surface group, pick a finite generating set, if they send generators to nearby matrices in PSL2R. In other words, think of this with the compact open topology. So I'm going to zoom out and look at this whole space all at once. And Goldman says, I know what the connected components of this are. This has a grand total of 4G minus 3 connected components. Okay, and how did I get 4G minus 3? That's all the possible numbers that satisfy this bound. Right? That's the number of integers you've got between plus and minus 2G minus 2. Okay? So you have exactly one for each Euler number. So these are classified, or what should I say? The Euler number is a complete invariant. So it's constant on connected components. And it distinguishes them. So if you want a cartoon now of what this space looks like, Goldman gives it to you. You can kind of, here, let's make a little chart of Euler number. Okay, it can be minus 2G plus 2, minus 2G plus 3, all the way up to, there's 0 in the middle here, a whole bunch of things, all the way up to 2G minus 2. And in each slot you have some blob. Okay. Exactly one for each. And we know what these ones are. Okay, so in particular, we know a connected space that has maximal or minimal Euler number. These exactly are the ones that come from discrete faithful representations. So, in one sense, this is saying that if you have a representation with maximal Euler number, it comes from like a hyperbolic structure on your surface. Just out of this invariant, there's some hidden geometric structure. Okay. So that's Goldman's work, and actually now we know sort of more what the shape of these looks like. I should give this a name. What is this space? People call this, okay, the PSL2R character variety. Okay. And that's a great name, except that it's not a variety. Okay, so, pi 1 sigma g, PSL2R quotient by conjugation isn't a variety. Actually, it's not even Hausdorff as a topological space, and typically, if you take a group and you look at homomorphisms from just some like discrete abstract group into, I don't know, G, a topological group, this could be a Lie group, whatever you want. Typically, this is not even Hausdorff. Like you can't separate different points by open sets. So it's pretty far from being an algebraic variety. Let me give you a specific example of the easiest way this goes wrong. Let's take, I don't know, gamma to be an infinite cyclic group and G to be SL2C. Okay, because now it's really easy for me to see what is Hom gamma G, or Hom Z SL2C. That's just SL2C, right? I just have to specify the image of a generator. And if I quotient by conjugation, this is just conjugacy classes of matrices in SL2C. Okay, and we all know exactly how to pick out a matrix up to conjugacy, right? This corresponds, the conjugacy class is given by the trace, right? That's just some complex number. Except there's one problem, okay, except if you have something like this, here's the identity matrix, it has trace 2. It is not conjugate to 1t, 0, 1 if t is not 0. Okay, but they both have trace 2. And if I think of these up to conjugacy, this is one conjugacy class, this is t non-zero, this is another conjugacy class. Because t can be arbitrarily close to 0, you can't separate these two conjugacy classes by open sets in the quotient. Right? So that's how this space starts being is not Hausdorff. Okay. But can't be separated by open sets. Okay.
So that's due to the fact that they're centered. Is that the only reason?
I don't think in general. So in here, what goes wrong, right? Here, what goes wrong is upper triangular representations in the same way. Okay, but if I put in a general topological group, I can give you examples that have no center where it's still something else goes wrong. Yeah. Okay. I mean, the point is conjugacy classes aren't closed, right? So that's what goes wrong. Okay. So here the failure is things that have upper triangular image, or something conjugate to this, or lower triangular. Okay, but let's fix this. Okay, so there's kind of an old school classical way to fix this, but eventually I want to talk about like groups acting on the circle, so I want to fix that isn't going to use anything like very Lie group specific. Okay, so here's my fix. You get something that's not a variety, or that's not even Hausdorff. Let's make it Hausdorff first. Okay, so. Oh, sorry, this is supposed to be I'm quotienting by conjugation. Okay. So if gamma is just a discrete group, and G is some topological group, okay, I'm going to define, okay, the character space, okay, of representations of gamma to G to just be, well, like take what you want to study, Hom gamma G up to conjugation, okay, but pass to a further quotient to make this Hausdorff. So take the largest possible Hausdorff quotient of this typically badly behaved space. Okay, so all you're doing is quotienting now by the closure of conjugacy classes, basically. Okay, it's easy to prove abstractly that any topological space has a largest Hausdorff quotient, with the universal property that any map to a Hausdorff space factors through this one. Okay, so you can check this as a little exercise. If you do this, then you really do recover just the complex numbers through trace. And in general, actually, so here's an old example due to Fricka. If you look at representations of, say, a free group into SL2C instead, it's now, this is a affine variety, if you like. This one is 2. It's 3-dimensional complex space. Studied by Fricka. And in general, if you take a discrete, if a finitely presented group, and you look at representations of that group into a nicely behaved Lie group, I believe you want a complex reductive Lie group, or its real points, then you get an affine variety. So in general, if anyone likes algebraic geometry here, the character space of a finitely presented group into, let me state a special case. Let's just say SLNC is exactly parameterized by characters of representations. Hence, the name character space. Okay. Great. Okay, so the classical way to define this, if you study these objects, is to take quotients, sort of algebraic geometry, quotients that come from geometric invariant theory. But like, here's a perfectly good, purely like low tech topology definition that happens to recover the objects people study. Okay. And I like this because now this suggests that if I want to understand these representations here up to conjugacy, my best hope is to look at this reasonable Hausdorff character space for Homeo of the circle and study that and try and get a global picture. This suggests, so to understand or classify foliated bundles, we should study the character space of representations of a group to homeomorphisms of the circle. Okay, and the whole rest of today, what I want to talk about is like what we know about this, what it looks like, and how to make some progress probing the space, which hopefully I pitched to you as a very basic object in mathematics. All right. Okay, so I pitched this as some kind of abstract quotient of representations up to conjugacy, but it's actually a completely natural object to study for other reasons. Okay, so things I want to tell you and explain. So here's a list of results, or what we know. Okay. All right, so I'll just make a list of things due to various people, and then we'll sort of explain who they're from and how they work as we go along. Okay, so one is points of this space are, well, they're not representations up to conjugacy. They're not quite conjugacy classes. They're something bigger. Okay. Are semi-conjugacy classes. of representations. Okay, and this works not just for surface groups, but for general, any kind of discrete group, representation from a discrete group to homeo of the circle. Okay. So I have to define semi-conjugacy for you, but let me postpone that to kind of give a global picture of what's going on first. Okay. What do I want to? Yeah, so this space, I did some magic to be like, okay, now my space is Hausdorff. What's nice about a space that's Hausdorff? Well, you have like maps to R or Rn or other, spaces that you can think of as giving coordinates or parameters on it. So actually this admits very natural local coordinates. Okay, which is also my goal to explain. Okay. And we don't quite have an analog of Goldman's theorem yet. So a classification of connected components for actions of surface groups on the circle. But we know a few things at least. Okay. We do know the picture is much richer. Okay. So the Euler number doesn't classify connected components. Okay, there's lots and lots and lots more examples. Okay, so maybe as a side note, if you fix the genus of your surface, you have something like at least, here I have what, 4g minus 3. Here I have something like 2 to the 2g connected components. But here's how little we understand. Possibly you could have infinitely many. That's a fascinating open question. Maybe we know what they all are. Maybe there's infinitely many and we just don't know, bundles up to deformation. And we do have a complete picture of all the isolated points. And it's a count of like isolated points in these things. These correspond to what? Group actions that have no deformations except by semi-conjugacy. Their semi-conjugacy class is like a whole connected component. Okay? So we actually know. We know that there exist a bunch of these, so that's a kind of a fascinating point if you're a dynamicist. So that's a rigidity theorem. Okay. And proving what these look like, okay, is what I want to talk about tomorrow. Okay, so the spoiler is that rigid actions or isolated points in these space come from when your surface group secretly actually goes into some Lie group sitting inside of homeomorphisms of the circle. Okay. So that'll be the theme. This is a result I proved with Maxime Wolf last year after 3 or 4 years of intense failure. But now we have kind of a nice clean picture that fits into this sort of long-term goal of proving Goldman's theorem in a bigger context. this is a natural set of questions to ask. Understanding this space is a much more natural set of questions to ask if you're, a topologist instead of a representation theorist, or if you do pure topology instead of geometry. Okay. Okay, so that's tomorrow. I want to talk at least about this much today and set up tools to use this so we can just prove a theorem all at once, or at least a special case. Great. Cool. Okay, this has been a lot of kind of setup so far. Questions? Okay, so now let's actually, give some precise definitions and prove some things and do some actual math. Okay, so what do I owe you to start? Let's talk about semi-conjugacy and why this is like a natural, dynamical invariant and what it is, because this is going to appear over and over again. Let's get let this marker rest for a bit. Okay, so maybe this is 1, and that's 2, and 3 might be for tomorrow. Okay, so definition. So maybe as a little side reminder, like recall that if I have 2 representations from some group to another group, row 1 and row 2, these are conjugate if there exists something in G such that row 1 of gamma composed with G, or I guess G inverse here, but I'll put it on the other side, is G row 2 of gamma for all gamma and gamma. Okay. Semi-conjugate comes in the special case where this is the group of homeomorphisms of the circle, and I'm going to take G to be less restrictive than a homeomorphism. I'll allow it to be a certain broader class of maps. Okay. So 2 representations. Actually, let me define this first. When we define rotation number, I was lifting things to the line. That will be very useful for us in the future. So let me define something in terms of lifts to the line. Okay. So if row 1 comes from as a representation of a surface group into the group of homeomorphisms of the line that come from lifts of homeomorphisms of the circle. Okay, so what is that? If my circle is R mod Z, these are exactly the homeomorphisms that commute with Z. Translation by integer amounts. So usually we write things invariant by a subgroup like this, the Z invariant homeomorphism, so I'll write it this way. So this is the ones that come from lifts. Okay. So if row 1 and row 2 are 2 representations of a particular group, sorry, this didn't have to be a fundamental group of a surface, this could be anything. Okay. So I'll define these 2 things are semi-conjugate if there exists some map from the line to the line. That's not quite a homeomorphism that came from the circle, but it's close. Okay, so what properties should this satisfy? I want it to look like it came from the circle. So that means h of x plus 1, it should commute with integer translation. So h of x plus 1 is h of x plus 1 for all x. I want to be weaker than a homeomorphism. So, but not just arbitrary. So I would like this to be monotone, meaning that if x is less than y, h of x is less than or equal to h of y. Okay, but less than or equal to, it doesn't need to be injective. And in fact, I don't even care if it's continuous. Okay. This guy, monotone, and I want that it looks like it's conjugating the two things. Rho 2 of gamma composed with h. Okay. So what you should think of is maybe h is something like, I don't know, here's on 0, I just have to tell you what it does on 0, 1, and then you commute with integer translation, so it should define it everywhere. Maybe you're something like, I don't know, like the Cantor staircase function. Okay. All right. Or, right, so that's some crazy thing that like collapses a whole Cantor set worth of intervals to points. Okay. Or you could be the inverse of this. Now, the inverse is not really super well defined. You could turn your head this way, and you're like, wait, that's not a function anymore, but just take out all the lines. Okay, and then you have the graph of a function, which is no longer continuous, but that's okay. That's allowed to be something like h also. So you should envision these kind of crazy things are allowed. Okay. And if instead you're going to the circle, it really doesn't matter. I want to sort of, it's easier to define if you take lifts. So rho 1 and rho 2, going from a gamma to homeomorphisms of the circle, are semi-conjugate if there exists an h just like above. Okay. And for every element of your group, there exist lifts of rho 1 of gamma and rho 2 of gamma to homeomorphisms of the line. Okay, so that these two things, the lifts of them, satisfy this conjugation property. So let's call this star. Okay, so you might be like, oh, why did I have to pick lifts to the line? If you don't, you'll get something that's a kind of a bad definition, and there's a whole paper written on how confused you can get if you don't do this, called something like on semi-conjugacy of circle homeomorphisms. But if you just make this definition, this is originally due to Gis, this definition sort of makes it easy, easy to work with and hard to go wrong. Okay, so this is closely related to what dynamicists say semi-conjugate means. They usually mean that you have two group actions or representations that are intertwined in this way, but by a continuous surjective map. This is not quite the same thing. Okay, so maybe warning, this is closely related to, but not, if you see the word semi-conjugacy in a different context, it's slightly different. Okay. Yet both of them are saying two representations or semi-conjugate means they capture sort of the same dynamical information. Okay. So maybe a couple examples. Okay, conjugate representations are semi-conjugate. Okay. If here's another kind of example to see that it can be quite different. If, I don't know, rho 1 is the trivial rep, so it just sends everything to the identity homeomorphism. Okay. And rho 2 satisfies the property that it has a global fixed point. Okay, so, and there exists some x such that rho 2 gamma of x equals x for all x. Sorry, for all gamma. Okay, so it looks trivial, but only on one point. Okay, then these are semi-conjugate also. Okay, via some map that takes everything to x and it translates. Okay, so let me draw the graph of a function on the line, or make it descend to the circle. Suppose my x that's a fixed point is, let's suppose it's 0. And I'm supposed to commute with integer translations, so that means I'll fix all the integer points. So every integer just gets sent to itself. Whoop. Okay. So I just want to collapse everything onto these regions. So here's a good map H that will do it for you. Here's a graph of a function. Okay. And you can check that if you plug this into there, this works quite nicely. So you apply H, anything gets sent to one of these fixed points, rho 2 doesn't move it. Okay, and if I apply rho 1, so it really is just the map H. And if I apply rho 1, I do nothing, and then I do H, so it's just the map H again. So so this is sort of picking up a global fixed point as a way of being trivial. Okay. An old example of Danjois an example he was studying is if your group is Z, infinite cyclic groups, you're really just thinking about one homeomorphism. He was understanding, what's semi-conjugate basically to an infinite order rotation of the circle. Okay. And if you use one of these kind of Cantor staircase semi-conjugacy maps, you can get something that behaves kind of qualitatively like an infinite order rotation, but an infinite order rotation has all orbits dense. Right? You can come back arbitrarily close to where you started. Okay? But you can get one that does not have this property by conjugating it by a map like this that takes intervals to points. Okay, so there are lots of interesting examples. I want to prove that this is a reasonable thing. So the reason for this slightly awkward definition is that it makes sense to say semi-conjugacy classes. Okay, so proposition, yo.
Can you give me an enlightening example why we cannot define semi-conjugacy just as like a semi-conjugacy in the homeo R?
Yeah. Right. So, so I want you to be semi-conjugate. Well, so what I want to prove is the next thing, which is proposition, is that semi-conjugacy, as defined here, is an equivalence relation. Okay.
Wow.
Okay.
You forced them to be symmetric.
So no, I claim that what I wrote down here is symmetric. It looks really not symmetric. Okay, so that's what we're going to have to prove. And if you write down sort of an analogous thing here on the circle, you get something that's not quite symmetric. And like so if H doesn't necessarily come from something on the line, you can get too many things being conjugate. So if you try and make it a definition that sounds symmetric, you can make everything semi-conjugate to the trivial representation by saying like collapse everything to a point. So the point here is that here you're like collapsing all the integers to you're sending everything to integer points. But you're sort of keeping track of if you're above or below. So if your guy really didn't have a fixed point and was able to move things around, H would then bump it up a level. And if you don't remember this data and you just send everything to a single point on the circle and like don't care about going back and forth, then you sort of the naive definition makes everything semi-conjugate to a trivial representation. This is the content of this paper that I mentioned by, so the story behind that is like doing this on the circle is a common misinterpretation, or there's a weaker thing you can do and say the equivalence class generated by, but it's the equivalence relation generated by, but it's a little unclear what you get. And people frequently just sort of were using a bad definition, and someone thought it was worthwhile writing down that like the definition that people write but don't mean like is a trivial relation. So yeah, it's a little subtle. But the nice thing here is that equivalence relation falls out quite quickly. Okay, so it makes sense to say semi-conjugacy classes, and this is what we want to study. Okay, so let's prove this. I actually want to prove something in detail so we can work with objects. So let's see, what do we need? Reflexivity. Okay, that's immediate. Take H to be the identity map. I need transitivity. And that's fine if there's some H that works for row 1 and row 2 like this, and I know another map K that works for row 2 and row 3, then composing H with K will give you what you want. Okay, so this is not hard. You just compose the maps that are playing the role of H. Okay, and symmetry is what we're going to have to work on. Let's do that. All right. Oh, and I should attribute this definition to Atinjis. Okay, so symmetry. So let's suppose you have row 1 gamma. Let's write it the same way I did there with the, oh, I wrote it the other way in my notes. Let's follow my notes. Row 1 composed with H is H composed with row 2. And this holds for all gamma in your group. And I want to find some map that will swap the roles of row 1 and row 2. Okay, so I'm just going to define, and if you had to do this on your own, okay, so your prototype Cantor staircase map, you want to define something that's going to look like the inverse of H, so that you can, you can conjugate the other way. And if this is what you're thinking of, there's really only one thing you can come up with, and that's the following map. So I'll call it, I don't know, K, that's a letter like H, from R to R, by, okay. I'm going to look at the supremum of the set of Y so that H of Y is at most X. Okay. And I claim that this satisfies all the properties here. Okay, this one, and it does a semi-conjugacy with the roles of row 1 and row 2 reversed. So the way it's written here. Okay. So let's check that this works. So first thing I want is that commutes with integer translations. K of x plus 1 is sup y. H of y is less than or equal to x plus 1. Okay, but H commutes with integer translations, right? So I can rewrite this as h of y minus 1 less than or equal to x. But that's equal to h of y minus 1. And if you feed this right back into the definition, this is k of x plus 1. Great, okay, so that's our first property. I want to check its monotone. Okay. And I think this I can just do from looking at the definition. H is a monotone function, or this weakly monotone. Okay, so if I look at the supremum of points that are less than a certain bound, and I compare two different where one is less than the other, I'll get supremums that are one is less than or equal to the other. So monotonicity follows from H being monotone. And now I want to check the opposite semi-conjugacy to this one. So let's figure out what happens if I do k composed with rho 1 gamma of x. Okay, it has to work out. This is the only kind of definition you could possibly make, but let's check it just so we really believe. So this is supposed to be supremum of y such that h of y is less than or equal to rho 1 gamma of x. Okay, and I want to make a change of coordinates to massage this so that the rho is on the other side or the k is on the other side. So I'm going to think of y as being rho 2 gamma of z. Rho 2 is a homeomorphism, right? So I can identify this with some point of this form. Okay. And so now this is h of rho 2 gamma of z. Okay. But h of rho 2 is rho 1 of h. So I can think of this as being rho 1 of h of z. Okay. Whoop. Don't use this notation if you teach calculus to freshmen. And let's see. Oh, and rho 1 is a orientation preserving homeomorphism of the line. Okay, so a point is bigger than another point if and only if. Oh, sorry, there's a gamma missing. Rho 1 of gamma is a homeomorphism of the line that preserves orientation or preserves order. So x is bigger than h of z if and only if their images under rho 1 are bigger than h of z. So let me rephrase that to say that this is the supremum of y equals rho 2 gamma of z such that h of z is less than or equal to x. Okay, great. I think I have just recovered. So this is what happens. This is k of something. Sorry. If I had a z here instead, I would recover k of x. But I'm actually taking rho 2 of that. So this is rho 2 gamma of x, of k of x. Great. Which is what I needed. Okay, so this is practice working with semi-conjugacy, and now you have this practice. Let me state an exercise, which is eminently believable, but maybe a little tricky in practice. Okay, but still worth working on. So exercise, or you don't like exercises, take it as a fact. Okay. The closure of a conjugacy class of a representation is a semi-conjugacy class. Okay. So this justifies exactly what we were talking about. The space we want to study is just semi-conjugacy classes of representations. Maybe now, yeah, question.
When we see the boundary of the closure, then is there any relation between interior point and boundary?
You mean that, like,
I mean, some homeomorphism, some sequence of homeomorphism make some conjugacy, then converges some.
yeah, right. So in particular, like if you have a map that's maybe not continuous or something like this, you can approximate it by homeomorphisms, right? This picture, right? So that's one way to get started on this. Yeah. Okay. Right. So I mean, the first step of this is you want to talk about approximating things by homeomorphisms, and then do this in a way that that shows that this is exactly the closure. There's not like overlapping semi-conjugacy classes. Okay. I think now we've gone a long stretch already, and I want to show pictures. So how about we take like a 3-minute break if you need to stretch or something. And then I'm going to talk about some recent work of Danny Caligari and Alden Walker that sort of draws pictures of this space in coordinates. So let's take a 3-minute stretch break or get coffee.